Myself, Dr. Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering in Dundigal, Hyderabad. Today I am going to discuss about the synthesis or preparation of glasses. So in this topic, laser glass spectroscopy, synthesis and preparation of glasses is the main role takes place in the laser glass spectroscopy. So last our previous session was discussed on different types of oxide glass systems. That is oxide based glass systems, borate based glass system, phosphate based glass systems, silicate glass systems, tellurium oxide glass system, germanate glass system. These are oxide based glass systems are discussed in last session. Now we are going to discuss about the synthesis and the preparation of glasses. Today outline of the today talk is on the first important of glasses. First topic is important of glasses. Second one is material selection. Third one is classification of glasses by preparation methods. Fourth one is preparation of glasses by melt quenching technique. These are the one of the important and prominent technique to grow the or synthesis or preparation of the rare earth doped glasses. Fifth one is different type of lanthanide doped laser glasses. So we are preparation of glasses after we are doping with different kind of lanthanide 3+ ions. That is the laser glasses. This last one is physical properties of laser glasses. So today we are going to discuss about the 6 topics. First is important of glass. Second one is material selection. Third one is classification of glasses by preparation methods. Fourth one is preparation of glasses by melt quenching technique. Fifth one is different lanthanide doped laser glasses. Sixth one is physical properties of laser glasses. Next, coming to the first one is importance of glasses. So glass exhibit the flexibility of choosing glass composition over a wide range. So we can choose the chemical composition, we can choose the wide range. That is one of the important property of the glasses. The second one is disorder environment that can broaden the fluorescence bandwidth. We can change the fluorescence bandwidth by tuning the environment of the composition. Next, third one is the uniform, that means isotropic optical properties over a wide range of composition. We can use different kind of compositions. At the same time, we can tune the optical properties in a uniform isotropic way. We can tune the optical properties over a wide range of by choosing the chemical compositions. Next one is the easy of fabrication into complex shapes including fibers. We can fabricate easily. So easy method is melt quenching technique. We can fabricate the glasses in simple way, even economically cheaper also. So complex shapes and including optical fibers also we can synthesize by using the glasses. So low fabrication cost which leads itself to mass production. So low fabrication cost which leads itself to mass production. We can produce the mass weight highly weight 2 kg, 3 kg, 5 kg, 10 kg of glass materials also we can prepare by using the chemical composition of the rare earth doped glasses. Just last one is possibility of producing large active laser media with good optical quality. That is flat shape, rod shape, disc shapes, different kind of shapes we can synthesize or fabricate the rare earth doped glass systems. These are the important properties of the glasses. Now coming to the second one is material selection. How we are going to choose the material selection. So the present selection highlights the facts, advantages behind the selection of borate, phosphate, tellurate and silicate glass systems for the present study. So we are going to discuss of these are the different kind of material selection. So first one is the borate glasses. In borate glasses, we are taking lithium oxide and cesium oxide, borate. So here B2O3, this is the glass former. In this borate glasses, glass former is B2O3, boric trioxide, boron trioxide, B2O3. So here lithium oxide and cesium oxide, these are the modifiers. So modifiers also adding into the glass former. Next, chromium Cr2O3, this is the dopant. we are adding the dopant is chromium this transition metal Cr2O3, chromium trioxide. That one we are adding as a dopant. So here borate glasses, B2O3 is the glass former, remaining rest of the composition lithium oxide and cesium oxide is the glass modifiers, and Cr2O3 is the dopant. So by doping the chromium dioxide into the borate glasses, we can prepare the borate glasses. So this is the one type of borate glasses. Second one is borophosphate glasses. So in borophosphate glasses, majority of composition is boron trioxide and P2O5. These are the glass formers. These both are the boron trioxide B2O3 and potassium pentoxide P2O5, because this is borate and phosphate. So both this is borophosphate glasses. So major composition will be boron. That means B2O3, boron trioxide. Next, after that, phosphorus pentoxide, that is P2O5. So these are the, we are taking major composition, B2O3 as well as P2O5. This is glass formers. In that we are adding glass modifiers is lithium oxide, potassium oxide, Li2 lithium oxide and potassium oxide K2O. These are the act as the glass modifiers. So here borophosphate glasses, glass former is boron and phosphate. At the same time you are adding glass modifiers as lithium oxide and potassium oxide. Here doping is manganese dioxide. Manganese dioxide is adding the, that is a low concentration. Here dopant are, you are taking around 1 to 10 mole percentage of composition only. Rest of thing are remaining. So we are taking glass former is a more percentage. If you are taking 100 mole percentage means more percentage you are taking glass formers. That is in the case of borate glass we are taking boron trioxide. In the case of borophosphate glasses we are taking major composition is B2O3 and B2O5. So less concentration, that means 10 to 15 or 10 to 30 mole percentage of concentration we are taking for glass modifiers, that is lithium oxide and potassium oxide. Dopant should be in the 1 to 10 mole percentage only. Not 10 mole percentage we are not using. In rare cases we are using. That means we are up to 1 to 5 mole percentage of dopant ions only we are taking in the preparation of glasses. So these are the important. Choose the material selection by preparing the borophosphate glasses. Next, coming to the third one is fluorophosphate glasses. Here fluorophosphate, that means here fluoride, we have to use the fluoride content will be, should be more, fluorophosphate. So based on the phosphate P2O5 and lead fluoride. So that should be very important. Major composition should be P2O5, phosphorus pentoxide, lead fluoride, PbF2. These are the measure, because that is why you are saying fluorophosphate, fluoride as well as phosphate. So P2O5 and lead fluoride we are using. That is the major composition for the fluorophosphate glasses. So P2O5 and lead fluoride concentration should be, you are taking more composition. If you are total 100 mole percent means, so major composition should be taken from the P2O5 and lead fluoride. Remaining are the glass modifiers, that is K2O and aluminum oxide and sodium dioxide Na2, K2O and aluminum oxide Al2O3 and Na2O. These are the glass modifiers in the case of fluorophosphate glasses. Here lanthanum oxide we are taking. This is the dopant. That is where lanthanum is samarium or dysprosium. These are the lanthanum doped glasses. That means samarium Sm2O3 or Dy2O3, dysprosium trioxide. These are the rarest ion or lanthanide ions. So that we are doping. This concentration should be 1 to 5 mole percentage only. 1 to 5 mole percentage of concentration we are taking into the preparation of fluorophosphate glasses. So major composition is phosphorus P2O5, phosphorus pentoxide, lead fluoride. These are the major glass formers. Next, glass modifiers is potassium oxide, aluminum oxide, sodium dioxide, and we are using dopant is lanthanum oxide. That in the case of lanthanum oxide in the fluorophosphate glass we are preparing samarium and dysprosium. These are the lanthanides. This concentration should be in the range of 1 to 5 mole percentage of rarest ion we are taking into the preparation of fluorophosphate glasses. Next, coming to the fluorosilicate glasses. This one is fluorosilicate glasses. In fluorosilicate glasses, major composition is silicate and fluorides. So zinc fluoride and barium fluoride and silicon dioxide. These are the important composition in the case of fluorosilicate glasses. Silicon dioxide we are taking more. That is glass former is silicon dioxide. Here more composition, more percentage of composition we are taking from silicon dioxide, and remaining rest of the thing we are taking barium fluoride and zinc fluoride. So lanthanum oxide here in the case of fluorosilicate glasses we are taking different kind of lanthanum ions, that is europium oxide, europium 2O3, europium trioxide, and samarium Sm2O3, and dysprosium Dy2O3. These are the lanthanum ions or rare earth ions of the different kind of glass composition. We are doping different kind of rare earth ions in the fluorosilicate glasses. These are the fluorosilicate glasses composition. Now finally we are taking oxyfluorotellurate glasses. Last one is the oxyfluorotellurate glass. Here in the case of oxyfluorotellurate glasses we are taking tellurium oxide. So tellurium oxide TeO2, zinc oxide, lithium fluoride and lanthanum oxide. So here tellurium oxide is the major glass former. Tellurium oxide. Next zinc oxide, lithium fluoride. These are the modifiers, glass modifiers. Lanthanum oxide in the case of oxyfluorotellurate glasses, we are taking the rare earth ions is dysprosium, erbium and samarium. These are the important rare earth ions doped with oxyfluorotellurate. These are the how we are choosing the material selection. So as per the glass preparation, we have to take the different kind of composition with respect to optimized concentration. There should be each and every composition should be, it will match with the 100 mole percentage. So we have glass formers, glass modifiers as well as modifiers or dopants. That should be in the uniform. We have to take 100 mole percentage. Total percentage should be 100 mole percentage. That is optimized concentration. That is optimized concentration. In the case of borate glasses or borophosphate glasses, fluorophosphate glasses or fluorosilicate glasses, oxyfluorotellurate glasses. These are the different kind of material selection while preparing the glasses doping with rare earth ions. Next, coming to the third one is classification of glasses by preparation methods. So this kind of glasses we can prepare different kind of methods or techniques. First, Jaroski reviewed various techniques of preparing the amorphous material. Amorphous materials is nothing but glassy materials. Amorphous materials is nothing but glassy materials. According to Jaroski technique, are prepared different kind of techniques. There is different kind of methods is there. As mentioned here, 12 techniques is there. In 12 methods, we can prepare glass materials. But well-known method is, first one is the well-known technique or method to prepare the synthesize and fabricate the different kind of rare earth dope glass materials. That is the first prominent method is melt quenching technique. Second one is thermal evaporation technique. This technique also using to prepare the glass materials. Next, third one is sputtering. In the case of sputtering also, we can prepare the different kind of glass materials. Next, fourth one is the flow discharge decomposition method. Also, we can prepare the different kind of laser glass materials. Next, fifth one is the chemical vapor deposition. This is CVD method. CVD chemical vapor deposition technique. Also, we can prepare the different kind of glass materials. Next, sixth one is the gel desiccation method. Seventh one is the electrolytic deposition method. Next, seventh one is chemical reaction method. In chemical reaction method also, we can prepare the different kind of rare earth dope glass materials. Next one is the ninth one is the reaction amorphization method. Also, we can prepare the different kind of laser glasses and irradiation technique. And next, shock wave transformation. In shock wave transformation method also, we can prepare the glass materials. Last one is shear amorphization method. Also, we can use to prepare the glass materials. These are the important technique to prepare or synthesize the different kind of rare earth dope glass materials. Among the all techniques, the well-established and versatile technique of producing an amorphous solid is the melt quenching technique. This is the standard technique. So overall, among the 12 techniques, the main technique and prominent technique to prepare the glass material is melt quenching technique. Melt quenching technique is the important technique to prepare the glass materials. Melt quenching means you have to heat the glass composition high temperature and suddenly cool down to the room temperature. That is called melt quenching. So we are taking different kind of chemical compositions and put in some crucible, and we are heating the sample at a higher temperature, suppose 1000 degrees centigrade. After this 1000 degrees centigrade to, we have to quenching from high temperature to room temperature. That is called melt quenching technique. So by using this technique, we are preparing the different rare earth doped glass materials. This is the prominent and unique technique to prepare the glass materials. That is called melt quenching technique. Now coming to the preparation of glasses by melt quenching technique. The usual way of obtaining glass is by quenching a melt obtained by fusion or one or more crystalline substances. When the rate of cooling is sufficiently fast to bypass crystallization, the disordered state of liquid is retained in the solid state. That is very important. So preparation of glass material, we have to, when the temperature is heating, after we are cooling down to the sufficiently fast bypass crystallization. So we have to, if slowly cooling means it will a chance to grow the crystalline structure in the glass material. So we have to bypass the crystallization property. That means we have to cool fastly, sudden cooling. That means high temperature to we have come down to the room temperature suddenly. That's fast cooling. We can prepare the glass material. Otherwise, we can slowly cooling means we can form the crystalline materials, not for glassy materials. That is the main drawback of the preparation of glass material by using the melt quenching technique. Next, all the chemicals used for the present work were procured from the sigma rich. With each and every chemical composition, we have to purchase highly purity. That means highly purity means 4N. That means 4N means 99.99% or 5N also 99.99. That means this is 5N. This is 5N 99.39. That means 5N. Now we are taking this method. We are using 4N purity. That means each and every chemical composition or each and every chemical we are purchased from the sigma rich, that purity should be in the order of 4N. That means 99.99%. About 25 gram of batch composition was thoroughly crushed in a agate mortar, and the homogeneous mixture was heated in a platinum crucible inside a electrical furnace. So we are using the melt quenching technique. We need electrical furnace required. At the same time, you need some platinum crucible and different kind of chemical composition. That means as per your class, if you are preparing the borate glasses, we need borate and remaining modifiers and a dopant should be there. So we require electrical furnace. At the same time, platinum crucible. Instead of platinum crucible, why we are using platinum crucible is to maintain the optimum glasses, and the purity is very very important. So we are using porcelain crucible, silica crucible, or different kind of crucible we can use. But in the case of platinum crucible, we can get pure glass material we can get, because there is no impurity in the platinum crucible. Platinum crucible also we can get the some more small percentage of impurity. In the case of porcelain and silica crucibles, we can get lot of impurities. That is why to avoid the impurity, we can use the highly homogeneous mixture was heated in a platinum crucible. That is a very important platinum crucible. See, the duration of melting and melting temperature are dependent on the glass composition. For phosphate-based glasses, the melting temperature range should be in the order of 1025 degrees centigrade to 1400 degrees centigrade in the case of phosphate glasses. And the duration of the melt is about 1 hour. So we can keep the temperature, the electrical furnace, we keep the platinum crucible with the chemical composition should keep in the temperature of 1400 degrees centigrade. Duration time should be 1 hour. We can keep 1 hour at the temperature of 1400 degrees centigrade. After 1 hour, we can pour into the, so the borate and tellurate based glasses, the melting temperature range should be in the 850 to 1000 degrees centigrade. In the case of borate and tellurate glasses, it takes low temperature, low melting temperature. That is compared to in phosphate and silicate glasses, this borate and tellurate glasses, its preparing melting temperature should be in the order of 850 degrees centigrade to 1000 degrees centigrade, and the melting duration is 45 minutes to 1 hour only. So we can prepare in this method, melting quenching technique, we can prepare different kind of glasses doping with rare earth ions or transition metal ions. Next, coming to the fourth one is the preparation of glasses by melt quenching technique. So first step we have to take chemicals, different kind of, you have to material selection, you are selected, we choose the material composition. That material composition should be, we take weight, minimum weight should be in the order of 8 to 30 grams. Each and every batch composition should be in the order of 8 to 30 grams. In the optical balance, we can take the composition of the weight should be in the order of 8 to 30 grams. After taking the chemical composition, we have to keep into the platinum crucible. So inside is there, this is the platinum crucible. So in that platinum crucible, we can keep all the chemicals. That all the chemicals we have weighed into the optical balance. Next, after that, we can crush that powder, fine powder, crushed with ball mill, or even physically also we can crush the powder with fine smooth powder. After that one should be keep into the platinum crucible. Then we can keep into the electrical furnace. In the electrical furnace, we can keep this is the melting temperature. This is borate or tellurate glasses or silicate glasses. We can use the temperature based on the composition of the glass material. So melting temperature should be 850 to 1400 degrees centigrade. So this is second step. After melting, duration time should be in the depends on glass composition. If borate glasses, we can use up to 45 minutes to 1 hour. If silicate glasses, more than 1 hour also. Like that, depends on the phosphate or silicate or tellurate or borate. Different glass composition, we have to choose the different melting temperature, at the same time melting duration also. After melting duration completion, we can pour into the preheated brass mold. This is the preheated, already heated. That means this brass mold already heated at 350 degrees centigrade. Because we are melt quenching technique, we are preparing the high temperature to suddenly come to the room temperature. If we suddenly come to room temperature, it will break or it will be completely, that glass material should be changed, all the optical properties. That is why we have to keep into the preheated brass mold, that is 350 degrees centigrade. After pouring into the brass mold, we can annealing. That means we keep into the 350 degrees centigrade for some 10 hours or 12 hours or 15 hours. Depends on glass composition. So after that, it will annealing. Why we are keeping for annealing? To avoid the thermal stress and strain. So we cannot break any glass properties. We cannot break any glass property. It will completely glassy nature, and also it cannot break. We cannot air cracks. Some cracks will be there. So to avoid that thermal stress and strain, we have to keep the annealing temperature should be at 350 degrees centigrade. After that, we can take it out. After annealing, we can take it out the glass material. Then we can go for the optical properties. First, we have to measure the XRD profile. First, after preparation of the glass material, we have to press that glass material and send into the XRD profile measurements. We can study the XRD curve, because we have to know this is a glassy material or crystalline material. Whether it is a glassy material means okay. Otherwise, we have to change the other glass composition and we have to prepare for other method. So this is the powder X-ray diffraction pattern of the glass material. So we can get all our sharp peaks only. That means broad peaks. That means broad peaks means we can shows that this is a glassy materials. So in this way we can measure the XRD profile. These are the important steps to prepare the glass material by using the melt quenching technique. First step is to weighing the glass composition as per required quantity, 8 to 30 grams. If you prepare the bulk means we can go for 100 grams, 150 grams also. At the same time, we have to choose the melting temperature should be very important factor, parameter. That is the based on glass composition. Your borate glasses means temperature, melting temperature should be low only. If you go for phosphate or silicate glass, temperature should be very high, 1400 degrees centigrade. After melting, we have to pour into the preheated brass mold. So in that is we are keeping for annealing at 350 degrees centigrade. To annealing, we are, that is main thing is to avoid the thermal stress and strain. That purpose we are keeping the annealing at 350 degrees centigrade. After annealing, we can keep the 350 degrees for 10 hours or 12 hours. After that, we can take it out to room temperature. Then that one you can polish and cut the glass material any required shape and rods, and we can send into the polished material. Then we can go for the optical and luminescence properties. First measurement we have to study for the XRT profile. So it should be a glassy nature or crystalline nature. So whenever we get in the broad peaks, means that is shows the this completely glassy nature or amorphous material. This is the preparation of glass by melt quenching technique. Next, preparation of glasses by melt quenching technique. The melt is then air quenched by pouring on into a thick polished brass plate and pressed with another polished brass plate. The glasses were annealed at a temperature slightly less than the glass transition temperature. This is very important. The glasses were annealed at the temperature slightly less than the glass transition temperature. If suppose in borate glasses, glass transition temperature should be in the 380 degrees centigrade. That is why we are using 350 degrees centigrade. It depends on the glass transition temperature and the different type of glass materials. Suppose if borate glasses we can use for 300 degrees centigrade. If you are using for phosphate or silicate glasses, we can use the 350 or 400 degree, because that should be that annealing temperature should be below the glass, slightly below the glass transition temperature. That is very important. TG value it should be less than the TG we can use to avoid the remove the thermal strain and stress. That is a very important thing. Why you are keeping annealing for the glass material? So that is the purpose is to avoid the thermal stress and strain, and we have to below the glass temperature. That is the very important parameter to prepare the glass materials. These samples were found to be stable at ambient condition and were well polished before measuring their optical properties. After preparation of the glass sample, we have to polish thoroughly and with a good condition. Then after that, we can send into the that glass materials to the different kind of measurements, optical measurements or luminescence measurements. Then we can study for the further luminescence or optical properties after preparation of the glass materials. Next, this is the different and various lanthanum doped laser glasses. These are the different kind of laser glasses. See here different rare. This green color shows the prismodium doped. This is the ND doped. This is erbium doped. This is prismodium doped. Different kind of doped rare earth materials. These are all erbium doped materials. This one is a different kind of rare earth doped glasses. Here, different shapes also there. These are the different rare earth doped glasses. We can prepare the different composition. That is, we are borate or phosphate or fluorophosphate or silicate or tellurate. That is different glass composition. In that, we are adding the rare earth ions or lanthanum 3+ dope glasses. Whenever active ion is added into the glass composition, it will exhibit the different kind of colors. So, in the case of if you dope with the prismodium, PR3+ ion, if you are doped means it can exhibit the green color. If you are erbium or yttrium doped means it exhibits this kind of color. If erbium completely this color source. So here different color, this samarium, dysprosium, this kind of colors also is exhibit. These are the different type of lanthanide doped laser glass systems. Next, this is completely europium doped laser glasses. This exhibit color will be white color only. This is a europium doped laser glass system. So this is a different size materials. So small one to high. So we can take 5 grams or 10 grams to up to 100 grams of glass composition. We can prepare the bulk glass materials doped with europium 3+. So europium 3+ doped laser glasses exhibit white color. So these are the different laser doped glasses and the same time europium doped laser glass. So this is the completely ND doped laser glasses. So this is ND doped laser glass. It exhibit like pink color. This undoped glass, this completely without dopant. Without dopant, it looks like white color only. So this is a rod shape and rectangular shape, different kind of ND doped laser glass. These are the used for the different kind of laser applications. We are using the ND 3+ doped laser glasses. The rod shape and rectangular or square shape of different ND doped laser glasses. First one is undoped laser glass. Second one is ND doped. Next, these are the ND doped laser glass systems. Next, we are going to study after the glass preparation, we have to study the physical properties of the laser glasses. First is the physical property that are important in characterizing the lanthanide doped glasses are density of the glass sample, concentration of the lanthanide salt, optical path length, and the refractive index. These are the important physical properties we need to study the after preparation of the glass materials. First parameter is density. Density rho of the glass sample was determined by using the Archimedes method, Archimedes principle. By Archimedes principle, we have to measure the density of the glass. So using the distilled water as an immersion liquid, that glass is poured into the immersion distilled water at room temperature means of following formula: rho equal W by W minus W1, where W is the weight of the glass sample in air. First, we have to measure that weight of the glass sample in air. In air condition, we have to measure, that is called W. That value you have to calculate. After W1, the weight of the glass sample in distilled water. Whenever that glass sample is immersed into the distilled water, at that time, what is the weight of the glass sample at room temperature 30 degrees centigrade? So, rho, by using this formula, rho equal W by W minus W. So, the weight of the glass sample in air, W1 is the weight of the sample in the immersion into the distilled water. So, W by W minus W1. So, we can get the density rho value. So, this is the first parameter, physical parameter to measure the glass material. Next, second one is concentration. So, concentration of the rare earth doped salt. How much concentration we are adding in the glass composition. So, lanthanide ion of glass composition will be how to measure concentration. Moles per liter was found from the expression. C equal formula is the concentration formula of the rare earth ion. How much dopant we are adding in the glass composition. That concentration we need to calculate by using this formula. C equal Y by MW. That means molecular weight into D by X into 1000. So, where Y equal to mass of the lanthanide ions. How much mass of the ions, how much 5 grams, 10 grams, and 15 grams, how much lanthanide ions we are taken into the glass preparation. That is the Y equal mass of the lanthanide. X is the total mass of the chemical composition. So, in the case of lanthanide, you are 5 grams taking means total composition how much? 25 grams or 30 grams. That is the total mass of the chemical composition. So, all chemical composition. This is mass is only for lanthanide dopant ion mass only. Weight of the lanthanide ion, how much grams you are taken. That is 2 grams or 3 grams. But this is the total mass, how much total composition, how much weight you are taking. That is the total mass of the chemical composition is X. Next, D is the density of the glass. We are calculating the density of glass. Next, MW is the molecular weight of the lanthanide salt, particularly for the lanthanide salt. So, samarium oxide or dysprosium oxide or erbium oxide, that lanthanide ion salt molecular weight we have to take. By using this formula, we can calculate the concentration of the lanthanide ion or rare earth ions. The concentration in moles per liter can be converted into ions per centimeter cube by multiplying with the factor of Avogadro number. So, we have to multiply with Avogadro number. Then we can convert the moles per liter into ions per centimeter cube. Ions per centimeter cube you can convert from moles per liter to ions per centimeter cube. This is in this formula by using we can calculate the concentration of the lanthanide ion or rare earth ion. First, initially you are calculating the moles per liter. After that one, we have to multiply with Avogadro number. That is, any Avogadro number you can multiple. Then you can get the ions per centimeter cube. That is the second parameter for the concentration. Next, third one is a refractive index. So, refractive index of the glass sample were measured using the IARE refractometer. So, Atago IARE refractometer using, we can calculate the refractive index of the glass material at a wavelength of sodium yellow line. So, here by using the sodium yellow line, that is 589.3 nanometer. This is a sodium yellow color, sodium yellow line. You can say this is yellow region, 589.3 nanometer. By using the wavelength of sodium yellow line with an accuracy of 0.001, the bromopenthalene was used in a contact liquid. So, in this particular IARE refractometer, we are taking the sample, we keep into the in this box. We can keep this sample. Then we can measure the at the wavelength, and then we apply the wavelength of sodium yellow line. At that time, we can show the value, how much refractive index we got. If borate glasses doped with the samarium 3+ ion, that how much refractive index, that is 1.5 or 1.43. Like this, we can get the refractiveness. In the case of heavy metal ion doped with the telluride glasses, we can get the refractive index will be more than 2. In the case of borate glass and telluride glasses, borate glass and phosphate glass, we can get value is 1.4 to 1.5 on the refractive index. In the case of telluride glasses, doped with the heavy metal ions, at that time we can get the refractive index more than 2.1. So these are the physical properties to measure the optical glasses. So first we have to prepare the glass composition and choose the material selection. After we have to prepare the glass composition. Next, after glass preparation, we have to polish and we have to measure for optical or luminescence parameters. First, initially we need to calculate the physical properties. That is the what is the density, what is the refractive index, what is the concentration of the glass materials. These are the important physical properties of the glass materials. So these are the citations cited in the this topic of the glass or synthesis of the glass materials. So these are the important references gathered from the synthesis or preparation of the glass materials. Thank you. Next section to be continued in the other parameters. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.